Well, I don't. What was the goal? Oh, find the second derivative, yes. 4x cubed plus 24 minus 1. I'm very slow. Okay, that's
24x.
24x. And that's the second derivative?
Yeah, the second derivative.
Okay, so you apply the reverse power rule. If prime of x equals x to the n, f of x equals x to the n plus 1 over plus 1 plus some constant. So this is going to be, so this is have to do it again. We don't know what that is, but it's there. That work?
Yeah, it works.
Okay.
Is that one of the homework questions?
Yeah, that was 31.
31.
If I'm not one wrong.
Page 360.
Yeah.
Oh.
Here we go. Really? 19? So what do we want to do with that?
I want to find the antiderivative.
So, a general point about finding antiderivatives, well, a few general points. One, some of them are going to be really straightforward. Oh, like the one that I erased. I mean, straightforward in that, you know, we have a tool to do it, the reverse power rule. There are many that are doable. Calculus students can do them, but the techniques to do them will not come till Calc 2. So if this is the end of the line, let me suggest in the future, if you run into a problem you don't really know what to do with, we're going to show how you do this one. There are references called tables of integrals that you can look up. Now, back in the olden days, we had books. You're a chem major. Have you read into the chemical rubber company book of chemistry numbers? You have. You check it out in the library. It's only about 50 pounds and about this thick. But in the middle of it, it's got a whole, like 20 pages of table of integrals that you can look things up. Most of the integrals in there, in Calc 2, you would learn the techniques that would figure them out. But for this class, you know, stuff that's straightforward, we're going to know how to do, and we're going to learn a couple tricks. Now, this guy, he looks intimidating, but there's a simple trick here. I'm going to rewrite this in a way that I think everybody will just follow directly. Okay. Now, at this point, we have enough information to do this. This is 5x. That's the reverse power rule. This one, you might not be so obvious, but 1 over x, we have to know that. We really have to know this one. This is the log of the absolute value of x. Right? Absolute value because, well, it works. If x is negative, then you can't find the log anyway. And here, I'm going to rewrite this once more as 4x to the minus 2. Again, you can use that. You can use the reverse power rule. So this is going to be 4x to the minus 1 over minus 1, or minus 4x to the minus 1. And don't forget constant of integration. So that's how you would handle this. This becomes a totally different problem if I go like that. And we're in a different world, and we don't know how to do that yet. This problem, it's kind of the same strategy. I'm going to rewrite it in a certain way. It's going to make it more doable. And here again, we can use the reverse power rule. And then, you flip these around, so forth. Fractions. So, if something looks, until we get to substitution, which we're going to get to in a couple weeks, all of these, if they look hard, then you have to reframe them. They should all be pretty straightforward. They should all be based on what we know about either the inverse power rule, derivative of the log. There is, I think I mentioned that if you have something like this, let me see if I can get it right. See some function to the n times its derivative. Well, let's think about what if we wanted to find the derivative of some other function. I'm going to say f of x to the m. Well, the chain rule and the power rule would tell me this is m f of x to the m minus 1 times the derivative of f of x. So the pattern you want to see here is you've got some function to some power times its derivative. And as soon as you see that, you go, oh, wait a minute. If I had f of x to the n plus 1 over n plus 1, and I find its derivative, it's just going to turn out to be this. So there's that pattern. This can be a little elusive too. If you see f prime of x over the f of x squared, well, again, you just want to think of this. This is f of x to the minus 2 f prime of x. And again, we can use the same strategy. So now we've got a negative. Or we might have a fraction, like we do in these problems. The one version of this that isn't so obvious, I'm just making a mess of the board here, but that's okay. But what if I have f prime of x over f of x? Now, it's really obvious the way I'm writing it here, what this is, but it could show up, like it could show up cosine of x over sine of x. Oh, did you notice that this is the derivative of this? Okay. Or, it could be x e to the x over e to the x squared. Well, that's too easy because you can just, oh, there we go, plus 1. What is the derivative of e to the, I guess I have to, x squared plus 1. What's the derivative of this? Well, it looks an awful lot like this. It's this pattern, except for a constant. So you're looking for these kinds of patterns. Now, what is this? What is the antiderivative of this? Well, it's just the log of the absolute value of x to the, yeah. Right? We find the derivative of this is 1 over f of x times the derivative of f of x. So, again, we're thinking backwards. We're thinking, well, when we find derivatives, what does the result look like? And again, there are patterns like this, or like this, or like this that you want to recognize. You also, see something like this, you think, well, maybe I can break it up into pieces, and maybe those pieces are all straightforward. And like everything else, do homework, just do a little practice, you'll see some examples of things, how they work. I guess something we haven't really done yet, which is give you some motivation for doing this. You know, at this point, it's kind of an exercise. We can find derivatives, we know what we can do with those. We can find velocity or change, rate of change. We can use linear approximation, we can use it to approximate a point nearby, a point we know. But the real point in doing antiderivatives, I guess we're gonna sneak up on that today. Any other questions? Okay, just want to check, see if I got everyone. Okay. Okay, that's something. Okay. This is not your second midterm. Oh, in case I don't really know how Canvas works. I know I put up an announcement, people mostly seem to get it. I put up the scores if you took the exam, put up the scores, so if you haven't, you can look up how you did. I will eventually get them back when all the other people hopefully take the exam soon. If you're chomping at the bit, you know, send me an email and I'll bring in your exam. We can go over it. All right. Before we get going, any other questions? Yes.
For some of the homework assignments, this is dependent on paper. In Canvas, it says missing. Is that going to affect our different?
Okay. If you turned it in and it says it's missing, please let me know. Will it affect your grade? Probably not. If you turn in no assignments, that's not good. If you turn in most of your assignments, that's fine. It's not gonna change your grade, one assignment missing. But I have seen other examples of this where my grader, you know, somebody showed me something that was corrected, they got it back, and it wasn't in there. So mistakes can be made, and all I can do is, you know, threaten her with bodily injury or something else. Just let me know if you see something missing and you know you turned in.
I mean, we could still, even if we get it back and it's like corrected, we could still upload it to Canvas anyway, no?
I think I heard what you said, and I don't think the answer is yes.
I got a homework back that was like corrected that I turned in on paper, but it was missing on Canvas, so I
Yeah,
still just
just
uploaded it.
let me know if you're feeling like defensive. Scan it and send it to me, but just let me know and I'll update it.
Alright.
Just tell me what assignment and.
I don't think any of the ones that I turned over.
You don't think any of them?
Yeah.
And you've gotten them back?
It's just Canvas.
Yeah.
Oh, you know what? Oh, I'm sorry. I apologize. So, just so you know, there's a separate document that my grader's keeping, the spreadsheet. She might have, I'll tell you what, send me that email, I'll go through her document and make sure everything is on Canvas. Is that fair? I mean, because that may be the problem.
Yeah,
Because
it's
hasn't been paying attention to Canvas because that's not where your grade is coming from. It's coming from this document. That might have been the case for yours. Yeah, send me an email, just remind me when I sit down in front of my computer, I'll fix that. Okay. So, hope this isn't a big surprise. The connection between adding derivatives, why are we doing it, is going to have a lot to do with area, not just area, things like area, like volume. And I wanted to, a lot of this will be redundant, but I just wanted to kind of go back to the beginning. Historically, area started to become important more than 4,000 years ago during the development of agriculture. I did this lecture last year, and I'm reading this really good book. If you're an anthropologist or a historian, called The New History of Everything. And it talks about this idea that is very prevalent in anthropological thought that, somewhere around, 6,000 to 7,000 years ago, we discovered agriculture, and then we became farmers, and then we needed governments and religion and all this other stuff. All the stuff that makes life awful. And that's the idea. But apparently it's not exactly right. People did discover agriculture in different places, but actually a lot of the previous economic system, which we call hunter-gatherers, persisted. It even persists to this day. So whatever I'm saying, not quite correct. But. Okay, so if you're a farmer and you wanted to purchase land, or more likely fend off, land with your weapons, you needed to evaluate, is 100 feet by 100 feet more than 200 feet by 60 feet. And we needed some math and some geometry. And of course, we didn't have feet back then. I guess we had cubits and other things. Most of what we know about area was known by around 300 BC by the Greeks. Hopefully you still remember some of the geometry you learned in high school. I'm gonna kind of go through some stuff hopefully real quickly about area. You start with the idea that you have some unit measure of length. And if you have a square, geometric object with 4 right angles, you just say that's 1 square unit. Okay, we can extend that if we have something that's, say, 2 by 3, right? We can break that up into units, and we get 6 square units. That takes care of areas that are made up of perfectly square units. But we can also use here real numbers. And so at least for something rectangular, we can calculate an area of any particular proportion. The next step is we want to know about something actually simpler, a triangle. Well, it's a triangle. What's the area of the triangle? Well, it turns out if you embed a triangle in a rectangle, you can see that the triangle is really just half of the area of the embedded rectangle. And so we get this formula that, I'm just gonna, I guess I'll use a capital B for base here, since we're using a small base, that the area is 1/2 base times height. That actually gets us pretty far, because now if you have some polygon, well, you can always break that up into triangles whose area you can figure out. So anything with straight lines as its perimeter, well, that's how we figure out the area of that. And then there's one more step we can go. We can take a look at a circle. We can think about, well, how are we going to figure out the area here with our rectangles and our triangles? Well, what we can do is we can break up our circle into triangles. We get an estimate, we can get an approximation, but of course we can put more and more triangles here. Each of these is just a piece of the circle. And eventually, as the number of triangles increase here, the bases get smaller and smaller, but the sum of the bases is the circumference. Right? So we have 1/2 the circumference times the radius. And as you probably remember, the circumference is, we decided, is 2 pi r, which we can substitute in and get our 1/2 2 pi r, or 2 pi r squared, or pi r squared for the area of our circle. The Greeks didn't have the idea of a limit, but you can think of, this creating these smaller and smaller triangles as some kind of limit process, the limit of which their bases becomes the circumference. All right, we're not quite done. There are other objects where we can figure out an area. Now, the cylinder, well, the bases of the cylinder are easy enough. Those are each pi r squared. But as far as the cylinder itself, you can kind of cut it, right, and unroll it. And it's basically a rectangle whose one of its sides is the length of the circumference. So we can figure out the surface area of a cylinder that way. Finally, we run into a problem that we really don't know how to do anything about. Which is you have a sphere. Well, there's no way to flatten out a sphere. It's not flat anywhere. You could try and approximate it. But you may recall from geometry that the surface area of a sphere is 4 pi r squared, but anybody where that comes from? I don't remember learning where it came from. That's something we can do now. We can do with calculus. The Greeks figured this out, but they used a strategy that was called the technique, the method of exhaustion. It already sounds difficult. You're going to get exhausted by using it. It's in a way similar to what we do with calculus, but not as rigorous, and they figured some of this out, but they didn't really have a strong foundation in mathematics in which to do it. So before I get through all this, I wanted to just repeat one formula which we're going to be using and is useful. What's the area of a trapezoid? Trapezoid has two bases, and it has height, and the area of the trapezoid is what? It's the average of the bases. It's one way to look at it, times the height. I mean, if you happen to have an isosceles trapezoid, you can kind of cut this piece and plug it in over here, and it's obvious that it's a rectangle. Or you could break it up into two triangles and a rectangle, and you could figure out the same thing. All right. So we're interested in a more general idea of area, some, there we go, that's kind of crazy enough. Some shape, and well, you could approximate it by drawing little squares or little rectangles, but it would be just an approximation. And for some reason, it's most calculus books think that this is really a very difficult idea to think of, the idea that this has an area, a measure, some kind of measurable area. But I'd like to suggest a rather obvious way one could interpret this. Let's say instead of a flat surface, this was kind of a dish. Kind of pretty serving dish for a soup or something. You take the liquid in this dish and you raise it to some fixed amount, like an inch, say an inch. And then you transfer the liquid to some other dish that just happens to also, liquid is also 1 inch. And now we have a rectangle, and we can figure out the area from that. It's not that complex an idea. Now, to figure out directly, without going through this process, that's something we're going to learn about in this course. That's just my intro to area. Now we'll get to the nitty-gritty. So the basic problem we're going to look at in calculus is we have some function, and we have 2 points on the function, A and B, and we want to know what the area underneath the curve between these 2 points is about. So how are we going to think about that? Well, we're going to start by breaking this up into, I'll call them slats for the moment. And we're going to approximate the area of these slats as trapezoids. They have a parallel side, and they have a height that we can measure pretty easily. So again, we're gonna go back and look at that area of the trapezoid being base 1 plus base 2 over 2 times the height. So let's just be clear on what those things are. Between any 2 points, we'll say A and A prime here. F of A and F of A prime are the bases. Height is just this difference. Just A prime minus A. That's our area of each one of these slats. Yes, this is not the notation I want to use. I actually want to give these names. I'm going to call this x0, x1, and this will be x sub n, maximum. And so this becomes f of, we're going to sum here. This is going to be the area of this is an area of the slat. So the area of the trapezoid is going to be the sum of f of x of n plus 1 minus plus f of x of n over 2 times x of n plus 1 minus x of n. And what are we going to take this from? We're going to take n equals 0 to m minus 1. So we're going to add up all these trapezoids. But of course, you know, we can keep adding more and more trapezoids here. And we'll get a finer and better approximation each time. For convenience sake, let's say that each of these x's is a fixed distance apart. We'll call that just delta x. So this then becomes and we also can say something else. We can say that delta x is e minus a over m. Yeah. In other words, this distance divided by the number of slats is what delta x is. All right. I'm going to do a little bit more with this. Let's just expand. We can take this outside since it's some fixed value. We can expand this And we can see that this is what? What does this sum consist of? Well, f of x0 plus f of x1 plus f of x1 plus f of x2 all the way out to f of x of m minus 1 plus f of x of m. And move the 2 out. So what did we decide? Delta x is e minus a over m, but we've got a 2 here, so 2m times this sum here. And now we want to think of, you know, what's the limit? What's the limit of this as n gets larger and larger? Is f(x0) plus 2 times f of x1 plus all the way f of x of m. We want to think about what the limit is. This is the way we're going to think of this in calculus. It's this limiting sum, which describes what happens as we add more and more of these trapezoids, as we break this up into finer and finer pieces. This is not that different from what I showed you with a circle, where we break it up into pie slices or pizza slices that are smaller and smaller and smaller. So, you know, how would we go about doing this? Well, one thing we could do is we could just stop at some m before it gets to infinity. We could do it numerically with a computer. We could add these all up. And we would get a pretty good approximation of the area. That's actually what, I guess we'll be doing a little of this in the class. If you have a calculator handy, that's fine. If not, I think we introduced this idea of the Calc function, where you put in a function and you get 7, and it asks you for A and B. And how does it do this? It's not using calculus, it's just adding up this sum over here. Okay, well, in any event, we're going to introduce this idea from calculus, which we call a indefinite integral. And here's how we write it. We use this fancy curve, which is meant to make you think of an S as in sum, summation. And we put in our limits, A and B. And then, you know, we put in our function. And then as a piece of notation, we write dx. You can think of dx as being, you know, the limit of delta x, delta x getting smaller and smaller, getting infinitely small. because we're using a limit. Couple of comments here. This is just notation, just like dy dx is notation. It's meant to make you think of, breaking your function up into infinitesimal pieces and multiply them by an infinitesimally wide trapezoid, but it's just notation. And also note that this x here is just a dummy variable. We could just as well write this t, t. We can change that letter to anything we want. It goes away in the summation. The last thing I want to make clear, this is an area, therefore it's a number. This is not a function. Once we've evaluated it, it's just some number. It's important to keep in mind, definite integral is a number. I'm going to write that. It is a number. Okay, so if you happen to have a calculator here, you might want to follow along. If you don't have one and you don't mind being too close to your neighbor who does, you can look over their shoulder. We're just going to do an example here. F of x equals x cubed plus 2x squared plus 5. And we want to know the area below this curve, whatever it looks like, between 0 and 5. All right, so let's go ahead. In the y area, I have to clear mine out. X cubed plus 2x squared plus 5. And what does the graph look like? Okay. So the graph kind of looks like this, so forth. And again, we're just interested in this area from 0 to 5. So we hit second calc. We say 7. Enter 0. Enter 5. And then, I don't know if anybody can see this from here, but the calculator does a little graphic. It fills in where the area is. And he comes up with an answer that I didn't expect, but that's okay. And go from 0 to 5 of x. I think I might have, either my notes are wrong or see what I enter. X cubed plus 2x squared plus 5. Okay, did anyone get anything any different? Anyone get anything the same? Anyone thinking of lunch? Okay. All right. Well, let's do another problem on the calculator. Let's take a look at the area from 0 to 2 pi of the sine of x dx. Let's try that. So that's pretty easy. Sine of x, graph it. Calc 7, 0, And you can use all your keys, enter pi times 2. And there it goes. And it tells me the area is 0. No. Anybody else get 0? Yeah, okay. Well, what's that about? Well, this is the graph of sine of x approximately. There's pi, there's 2 pi. So there's kind of a lesson here. Area above the x-axis is positive. Area below is treated as negative area. Now, I don't want to get into philosophical discussion. There's such a thing as negative area. No. But this is the way an integral works. So it's going to treat this as a negative. It's going to subtract from this. You could do an integral and get a negative number. Now, let's say you really don't want that. You really want to know what the area is here and here. You can just do this on the calculator. You can find the absolute value of the sine of x. So I will. You don't know where the absolute value is? Second down below, there's a thing called catalog. There may be an easier way, but the first function that comes up is absolute value, sine of x, and I get a little function that looks like that. Calculate 7, 0, 2 pi, and instead I get 4. Okay. All right, so need people here taking statistics. Anybody here going to take statistics? Anyone? All right. Well, this is good information if you're interested in math. Any social sciences, you're going to come across some statistics. And you may have run into a function that looks kind of like this. I'm not going to reach the axis. So, sometimes called a bell curve. Normal distribution. And the equation of this function is f of x equals e to the minus x squared. I want to do just a little experiment here just because it's fun. I want someone to plug this equation in and find the integral. I'm picking these numbers minus 5 and 5 because by the time you get to 5, this is almost at the axis. It's most of the area. It'll approximate it pretty well. And I'll try it myself too.
How did you get the 2 pi into the upper limit?
Over here?
When I tried to do it, it just has like an error.
Oh, okay. So, yeah, this is a calculator thing. Try this. Go to second. No, I'm sorry. Just go to Window. No, not Window. Go to Zoom and hit Zoom 6. Zoom Standard. These calculators are funny. Sometimes when your window doesn't quite match what you're integrating, it just goes crazy. It doesn't like that, and it'll give you that, you know, quick or retry kind of error. See if that fixes it. All right, on to e to the minus x squared. I don't know if I did that the way it wants it to. Minus x squared. I'll know pretty quick because the graph will look good or it won't. Might want to zoom in. Yeah, again, you know, it's just a nice little graph here. One. Oh, of course, 0, this is 1. So, again, any of you who are with me on this, calculate 7 from minus 5. Oh, I have to zoom out first. Zoom out. Try again. Calc 7 minus 5, 5. Okay, anybody with me here on that? I get a number 1.772459. Anyone else see that? Okay, so here's it. Just want to show you a little trick because it's kind of fun. So hit second answer, and it'll pop up. It'll pop up answer, and now square that. Up arrow 2, and what do you get? Does that sound familiar? Yeah. Yeah, the area under this curve is actually the square root of pi. Kind of a weird thing. Before we take a break, I just want to say, the reason I bring this up, a really important function, really important in statistics. This tells you a lot about a normal distribution. You know, you can figure out like the probability of certain things happening using this curve. But we are not going to be able to use calculus to find this area. It just isn't going to work. We can use numerical methods. We can use our calculator. And if you take a stats class, you may find either a table or you might even find a function on here that's going to do this for you. But it's not going to be doing it directly. It's not just going to be, we're not going to find some function to plug in to get these areas. All right. I'm going to take a break and we're going to come back and we're going to do stuff a little more meaty. All right. Any questions? No? This afternoon is going to be a little shorter than usual. I'm going too fast. I think I know we have a few math majors in class, and in a few semesters, stay with math, but you're going to take a course called analysis, during which they're going to describe integrals, and you're going to see that they've kind of been lying. They're not a little white lie, nothing important. But the way we rigorously define an integral is a little different from what I've said up till now. It's probably not going to seem all that important. It's still a sum. From 1 to n, where n is getting larger and larger. And it's just a function defined at some x, which I'll describe. I guess times some delta x. We don't really restrict the width of these to be specific value. We're just going to add more and more. We're going to make this tighter and tighter. And we don't actually use a trapezoid. We just pick some point in the interval. This x asterisk, just a member of that interval, from x I minus 1 to x of I. It's just somewhere in between here. And that's what we define as this definite integral. This is not real important to most of you, and just truth in advertising. Mathematicians, when they want to prove something rigorously, can be very particular. Just a reminder, of course, this is a number. It's not a function. So I want to start off with just a couple examples, some really simple examples to kind of lead us to where we're going with this. And look at the function f of x equals some constant. So we want to know about this area here. We don't have to use this fancy definition. It's pretty obvious. The area is just going to be b minus a times c. This is the area of a rectangle. One side is c, and the other side is b minus a. We could write this as using the following notation, either x times c from a to b, or you could also write it this way, x times c from a to b. Where it's understood, we just, x is a variable here, we plug in b times c, and we subtract a times c, which is just what this is, bc minus ac. But we know that the antiderivative of f of x equals c is of x equals cx. Is maybe coincidentally just what we have here. Okay, just one simple example. I guess I should write this cx, make it look a little cleaner. All right, well, that's nice. Let's do another example. Another simple example. Let's say we take the function f of x equals x. And we want to find this area here. Well, this just happens to be a trapezoid. This point here is f of a, this point here is f of b. This is b and a. Well, we could think of this as this large triangle minus this smaller triangle. So this large triangle is, base is b, the height is b, so b squared over 2. And the smaller triangle here is, of course, a squared over 2. That's our area. Well, again, using the notation I described previously, we could write this as x squared over 2 from a to b. But once again, we note that the antiderivative of our function just happens to be using the reverse power rule, x squared over 2. So it starts to look like this is more than a coincidence. We have the idea of this integral, some function, and the notion that there's an antiderivative, whose derivative is our function. And starting to look like we can evaluate this definite integral as the difference between the antiderivative evaluated at b minus the antiderivative evaluated at a, or again, using this notation, it's starting to look that way. And of course, that will turn out to be the case. We're going to find that we have some function. If we can find its antiderivative, then we can evaluate a definite integral in just this manner, which clearly is the case for these simple functions, f of x and equals x and f of x equals c. Just I guess it's just going to be that way today. It's an unusual day. I don't really want to go further today. We're going to come back on Thursday and actually show this in a more rigorous manner. Provide a convincing argument for why this should be the case. But I feel like we've kind of gone over enough today. So I'll hang around for a while if people have other questions, homework, or they want to discuss anything, midterms, finals, calculus.